This is the new single band compressor. The compressor has undergone a major rewrite. In order to avoid blowing up the speakers of the one guy who uses this program, the new compressor ignores the settings for the old compressor and uses the default parameters. You can still edit the XML to convert the old parameters, but using the old parameters directly will blow up your speakers. The compressor shows the current trigger value in the in meter and how much gain is being added or subtracted in the gain meter to reach the desired output. It can be attached to a single track or multiple tracks. The compressor is a multi-channel effect. Any of the tracks can be a trigger. The gain adjustment is applied to all the tracks. Here we have audio with very wide dynamic range that desperately needs limiting. The compressor plugin either expands dynamic range or limits dynamic range. Most often, we use it for limiting dynamic range to make sounds more even. The compressor determines the smooth trigger level and converts the level of the smooth signal to the output indicated on the sound level graph. For each input level, we have an output sound level defined by a rubber band line. Obviously, professional compressors have dials to adjust the gain values while listening for changes in real time. To save space and more clearly visualize the parameters, we went with a graph. Here's how you edit the compressor graph. Left-click anywhere to create a point. Click on a point and drag it around to adjust it. Drag any point across another point to delete it. Let's make an expander graph. To get the output level to rise twice as fast as the input level, draw a line that rises 12 dB for every 6 dB. Hold Shift to make it snap to the grid.
You're coming together.
This makes it work like an expander.
Is your undoing.
What are you doing there, 3PO?
To get more precise graph points, dial them in the output and input text boxes. For the expander, you want to cut off below a certain minimum input. Above the minimum input, it needs to rise faster than 6 dB for every 6 dB horizontally, so you get a steep vertical line. It's not possible to get a perfectly vertical line. If you try to create a vertical line, it'll delete the points instead. The levels below the minimum input are automatically passed through unchanged, but since they're already at the minimum value of the graph, they're essentially muted. Now we'll make a limiter. To get the output level to rise half as fast as the input level, draw a line that rises 6 dB for every 12 dB horizontally. Now it's keeping all the sound levels too quiet to hear, so we have to add makeup gain. Raise the vertical offset of the line to add makeup gain.
We're not alone. Good people will fight if we lead them.
Sometimes you want all the output to be clamped at a certain level. This requires creating a horizontal line. The trick here is you need to create 2 points to make the line horizontal.
We're not alone. Good people will fight if we lead them.
The typical compressor usage is making everything sound as loud as possible. This starts with a horizontal line at 0 dB. The bottom point is where the sound is gated. Below the bottom point, the sound is passed through unchanged. Shifting the bottom point left and right is the equivalent of adjusting the makeup gain. No makeup gain. Lots of makeup gain.
You're coming together.
Another usage of the compressor is noise gating. This is normally used to isolate voices with lots of background noise. Let's load a noisy voice track. Let's clear the compressor to reset the graph. Based on the input meter, we see lots of noise around -20 and transients up to -10 for the voices. So we'll create a noise gate around -20. And then above that, we'll define 2 points so the audio passes through unchanged. But we still have a hard time hearing because the voices need extra makeup gain. Let's add some makeup gain by raising the minimum point. Crush all the wanted levels to 0 dB. And maybe pass through more of the signal at the noise level.
More technology forces in the stable, essentially, to make to use in order to get humanity.
So here it's cutting off basically everything that's well within the noise floor, and everything above the noise floor, it's crushing right against 0 dB by adding a lot of gain.
I only thought there was maybe a 10%.
The big difference between this and the old compressor is there is now a headroom on the sound level graph. For inputs above 0 dB, the old compressor would always crush them to 0 dB. The new compressor allows users to define the result. The default, if we don't define a point for the headroom, is to merely extend whatever the slope is below 0 dB to the entire headroom. You now have to define another point to define what happens over 0 dB. So with this extra point, you can make the level above 0 dB be limited, pass through unchanged, mute, or expand. Now that you've seen the amplitude domain, it's time for the time domain parameters. The attack time says how far ahead of a peak the smooth level starts rising. The typical value is 0.1 to 1 second. The release time says how long after the peak the smooth level falls. The typical value is 0.1 to 5 seconds. To make sounds louder, shorten the attack and shorten the release. To make sounds quieter, lengthen the attack and lengthen the release. To make the compressor less obtrusive, use shorter attack times and longer release times. Watch what happens to the gain meter when we adjust the attack and release times. With 0.1 and 0.2, we see the gain meter fluctuating wildly. Let's adjust the output levels so the gain is more visible on the gain meter. Now when we lengthen the attack and the release, you'll see the gain meter slow down dramatically. It's taking a lot longer for the smooth input signal to track the peaks. If we set the attack really short and the release really long, you'll see the gain meter suddenly fall and then rise much more slowly. The fall of the gain meter is the beginning of the peak where it's applying the attack time. The rise of the meter is after the peak where it's applying the release time. A typical demo is to render a pulse, showing the sections before and after the pulse getting softer and louder as the compressor smooths out the level. So here we have a pulse that goes from -6 dB to 0 dB and back again. Let's apply the compressor to this pulse. We're going to make the compressor amplify everything and limit the output to 0 dB. We'll set the attack time to 1 second and the release time to 5 seconds and render the result. Here you see the compressor is compressing everything against 0 dB. 1 second before the pulse, it starts fading out over the attack time, and then after the pulse, for 5 seconds, it's fading back in over the release time to try and keep the output at 0 dB. Notice at the beginning though, we have 5 seconds where it's increasing the gain. That's because the compressor starts with 0 gain, and then it uses either the attack or the release time to determine what the true gain should be. Another way of visualizing the compressor's operation is the Smooth Only button. Let's enable Smooth Only and render the pulse to a new track to see the smooth dynamic level as a new waveform. So here we see the smooth level of the trigger waveform as a line. It starts as 0 dB and goes down halfway because the true signal is -6 dB. Then, an attack time before the pulse, our smooth input level starts rising back to 0 dB. After the pulse, as our input drops back down to -6 dB or halfway, our smooth level over the release time drops back down halfway. The old compressor used negative attack values to read ahead and positive attack values to lag behind the peaks. The new compressor takes negative or positive values for compatibility, but only reads ahead. The lagging mode ended up never being used, so the new compressor always reads ahead exactly the way Audacity does. The trigger type determines what track is used for the smooth input level. It can be a single track in trigger mode, a sum of all the tracks in total mode, or the maximum of all the tracks in maximum mode. When the plugin is attached to multiple tracks, the trigger mode can use any of the tracks. When it's attached to a single track, the trigger type is meaningless. It always uses whatever track it's attached to. The output gain of the compressor is always applied to all the tracks, including the trigger. Let's load a sound file with very similar tracks to show the effect of the total trigger, and apply a 0 dB limiter. Notice the output levels all specify 0 dB for the desired noise levels, but our gain meter is showing it taking away gain. Turns out that the total trigger is adding both tracks to generate the trigger, and when both tracks are nearly 0 dB, that means the trigger is going to be well above 0 dB and even 6 dB if both tracks are the same. It's going to need to take away gain to get 0 dB output. If the tracks are similar, the total trigger tends to make the output half as loud as either track and make the gain meter take away gain. If the tracks are vastly different, the total trigger makes the total volume more even. If the tracks are being downmixed into a single channel, the total trigger can prevent overloading. Now let's change to a maximum trigger. You can see the gain is always amplifying because it's using the loudest track, which is usually below 0 dB. The maximum trigger uses either track depending on which track is louder. If the tracks are being output into separate channels, use the maximum trigger to make the song louder but less even. If the tracks are being downmixed into a single channel, the maximum trigger will cause the output to be overloaded. Now let's attach a unique compressor effect to each track, instead of sharing a single compressor between both tracks. The trigger type has no meaning because each compressor is processing only a single track. This gives the absolute loudest output. Unfortunately, it causes the sound to randomly pan between the speakers. It could be useful if you're downmixing to a single channel, want the absolute loudest output, and don't care if one input track or the other has the majority of the sound. There is also triggering off a fixed track number. So let's create a new track to be used purely as a trigger and use our previous other two tracks as the sound to trigger. We'll set the trigger track to track 0 for the topmost track. The standard use of a single track for triggering is to make the music only play when another track makes sound. The simplest trigger track is just a synthesizer where we modify the frequency to stop and start a pulse. The synthesizer is off when its frequency is 0, and it's on when the frequency is non-zero. We don't really care what the frequency is because it's just being used to turn on and off the music on another track. And then we want to set the compressor as a noise gate, so when there's no sound on the trigger track, the compressor is going to mute it. When we do have sound on the trigger track, we want the compressor to pass through the music unchanged. So that'll be a 1-to-1 rise of the output. Also notice when we start playing, the compressor still starts in neutral gain until over the release time it establishes the true trigger signal. If you don't want to hear the trigger track, mute it. The compressor is still running, but the trigger track is muted. In the next episode, we'll discover the multi-band compressor.